rounders. It's a pretty neat one. It's really math oriented, so that's always fun. I guess let's go ahead and dive in. So we want to turn the given integer into a number that has only one non-zero digit using a tail rounding approach. Okay, so first of all, before we go any further, integer, whole number, right? So we're given a whole number. That's what value is going to be. We want it to have only one non-zero digit, and we're talking about a tail rounding approach. So basically, we'll talk about tail rounding approach in just a sec, but first of all, having only one non-zero digit, basically we want to have some digit, like let's say 5, followed by some number of zeros. Maybe it's just 1 0, maybe it's no zeros, maybe it's 100 zeros, I don't know. The point is, we want to round it using this tail rounding approach. So what do we mean by that? Well, basically at each step, we take the last non-zero digit and we round it to 0 or to 10. And so basically the idea is that we sort of keep rounding the number, you know? So like, it's like we take, for example, 1,234. We round it to the nearest 10, so this is a 4, so we'd round down, so it would round to 1,230. And then we take the 30, round it to the nearest 100, round that down, so it's like 1,200. And then we round the 200 down because we want to round to the nearest 1,000, and the nearest 1,000 is 1,000. Whereas if we take something like 1,445, we wouldn't expect it to really work this way, you know, because like if we're rounding a number, this would normally round down to 1,000, but using this tail rounding approach, it's rounding up to 2,000. Okay, so that's a little bit different. That's kind of neat. So let's think about how we can deal with this thing. Basically, I mean, what we usually do is sort of take a literal approach for our first attempt here. So we'd look at it and basically say, okay, let's write something with a loop that's just going to keep rounding the number down over and over and over again until it can't anymore. So we could do something like that, and then who knows, maybe there's going to be some other stuff we can do too. So how are we going to do this? Well, basically, let's think about how we would round a number just in general. Like if we were to just do Math.round, which is a thing, a value, it's not really going to change much, you know? There's nothing really to round here. I don't know if we can give this like another argument or something like that to, you know, specify, like I want you to round to the nearest 100 or something like that. That's maybe worth looking up. But the sort of, the way I'm used to doing it anyway, and the way we do this in terms of math, is if we wanted to round to the nearest 10, we'd divide by 10. So basically 15 divided by 10 would give us 1.5, so that should round up to 2, but then we want to multiply that by 10, so that it should round up to 20. So let's run this one, and now, yeah, it's passing that first test, it's rounding up to 20. The problem is, well, actually, wow, it's passing 4 out of these. That's pretty impressive, I guess. But the problem is that not all of them want to be rounded to the nearest 10. Some of them, it's the nearest 1,000, some would be the nearest 100, but I guess a lot of these are the nearest 10. Anyway, point is, even then, like, okay, let's say we do want it to the nearest 1,000. Yeah, so 1,000 over here and 1,000 over here. Is this even going to work is the question. So first of all, it's probably not going to pass those 4 that it was passing before, those 4 out of 6. So yeah, as suspected, not passing that. But okay, it is passing this one, but this was another 1,000 one. Shouldn't it be passing this one? Well, no, like we saw before, it's not just a matter of simply rounding down to the nearest 1,000 or rounding to the nearest 1,000. We have to do it systematically, sort of one step at a time. That's kind of the idea here. Okay, well, could we do something like this? How about we say like for let power be assigned the value of 10, and we'll say while power is less than value. I might end up changing that, I'm not sure. And then at each step, instead of a plus plus, we're going to say power times equals 10. So this will be like the 10, the 100, the 1,000, the thing that we're going to divide by and then multiply by in order to do our rounding. So you could do something like this, like maybe value is assigned the value of, oh God. Okay, this is why I don't usually like using the word value for a variable name. But anyway, This thing is assign the value of what? Well, what were we doing before? We were saying basically something like this, right? 10 times math.round value divided by 10. Except now in this case, it's not necessarily going to be 10. It's going to be more generally power. So let's just fill that in. And whoops. Let's get all the letters in there maybe. Yeah, good. Okay, cool. And then at the end, let's return value and we'll see what happens with that. Oh, okay. So that was enough then. That's good. Very good. Nice job. Okay, great. So that's passing all the hidden tests. No issues there. Oh, hey, thanks. That's always nice. I'm wondering, should we look this up? Math.round, just to see if there's like a better way to do this? Like if we could just give it a second argument or something like that? I don't know. Is that a good idea? Let's look it up. So JS math.round. Let's just try that. Oh, looks like I've been here before. Okay. So I should know, in other words. Oh, okay. So this is how much precision around it with. Yeah, this is exactly what we want. So -1. Oh, wow. Okay, so could we just do like... Could we just do this? Hold on a sec. Wait. Hold on a minute. Before we even get into that, let's just say return math.round value -2, let's say. Let's try running that one. Okay, so that's giving us 15. Wait, does that make sense? I feel like these aren't what I was expecting. Because this kind of gave me the impression that, oh wait, maybe -1 is what I want. Let's try -1. Let's give that a try. Maybe it's because the numbers were too small there. No, I don't know. That's weird. This one was definitely giving me the impression, oh, sorry, that's precision round. Oh, okay, so, oh. Well, geez, you got me all confused here. Okay, so precision round isn't a built-in, I guess. It's just this thing that they built over here. Well, okay, well, that's just what I'm doing, man. Jeez. Okay. I'm gonna get my hopes up. Well, hold on a sec. What are all these? Round 10? Okay, that's another, like... That's not a built-in, is it? Round 10? They're just sort of showing you, like, how you would do that, I guess. All right. Let's switch back to this. I think we're probably okay with this. Let's just, how do we have it? Let's just do a bunch of undos. Was it like that? Is it like this? Does this work? Let's find out. We'll see. In the meantime, while we're waiting for that to run, I wonder if there's other way to do this. Because I'm sort of thinking like, you know, we're dividing by 10, rounding it, and then multiplying by 10, right? And then we're dividing by 100, rounding it, and then multiplying by 100. So could we like, maybe we could do this a little differently. Let's reset the code. Let's paste this back in. This is going to be rounders 1. And in fact, actually, wait, I didn't need to reset the code. Oh, well. So, you know what? Here's what I'm thinking. Okay, I'm going to keep this part the same for now. But for over here, so value is going to be power times that. I'm thinking, what if we did something like this? What if instead of this, we didn't multiply it by power? You know, we didn't multiply it back in. And instead of dividing by power, let's just divide by 10 each time. And in fact, let's declare power outside of the loop. Okay, so we're going to get this out of here and put it up here. Yeah, okay. And then we want to return the value at the end of this, and it's probably going to be some floating point like decimal number. Oh, wait. Oh. Is this what we want? No, this is definitely not what we want, eh? Okay, so what happened here? We were doing value divided by 10, and then we were rounding it, right? So it stopped. Why did it stop? This started at 10. Multiplying by 10 each time. Okay, so let's see what happened here. This would be good if we just multiplied that by 10, right? This one would not, though. It's maybe stopping too early. It's rounding it to 12. Maybe let's get a console log and see what's happening at each step. Basically, my plan here, and the reason I wanted to take power outside of the loop is because I want power to be sort of this number that's going to just get bigger and bigger, and then at the end we'll multiply power times value. That's going to be sort of the idea. Why are we going to do that? Well, basically so that we don't have to keep like dividing it and then multiplying, then dividing it, then multiplying, then dividing it by multiplying it. Because basically we're dividing by 10, multiplying by 10, dividing by 100, multiplying by 100, right? So what I'd prefer to do is just divide by 10, and then divide by 10 again, and then divide by 10 again, and then divide by 10 again, and then multiply it all by 1,000 or 10,000 or however many times I said 10. Anyway, the point is, that's sort of the plan. Let's see what's happening here. We're getting 2 console logs here. So it's going in, basically it's saying we've got 1, 2, 3, 4. We divide that by 10. It's 1, 2, 3, 123.4. We round that, so it becomes just 123. Done. Okay, so we're good with that. That makes sense, right? And then the 12 one. Okay, so let's see. Yeah, I think that makes sense as well. Oh, you know what? Maybe it's just that I have this set to a 1 when it should be something bigger. No. Okay, so what's going on here? Oh, right. Yeah. Okay, so my mistake. This isn't going to work because I'm saying power is less than value. I could maybe say something like initial value is assigned the value of value. Oh, God. Yeah, and then put initial value in here. That should work better, I think. I think that would make more sense. Yes. No. Power needs to start at 10 for that to be the case, I think. Or, well, okay, we'll do it this way for now. Yeah, so it stops there, Good. Very good. And then over here, we just want to multiply by power, and then I think divided by 10, because I think power is going to get multiplied one too many times here, I'm thinking. Let's see, because in this case, we run the loop once, right? So that means power starts at 10, we multiply it by 10 again, it'd be 100. So when we multiply power by value, it'll give us 200. We want to divide by 10. So let's give that a try. We'll get rid of that console log. Ooh, yeah. Okay, cool. So this is working good now. Nice. And, let's see. I should probably put a semicolon on that. The only part here that I'm not super fond of is like this initial value thing. Maybe let's instead let's keep this part value. And we'll just call this like leading, or yeah, leading, as in like the leading digits. I don't know. Yeah, we'll call it leading. That works. Okay, so leading, and then it starts as value, and we're just doing this. Okay, cool. Great. That makes sense. Okay, cool. So this is good, right? I think this is working. Well, actually, have we tried the hidden test? Yeah, okay, it's working. Good stuff. So I want to think about something here. I want to start thinking about a more direct approach, because sort of the theme of the loop tunnel here has been that we've been sort of trying to avoid loops, you know? Like, if we don't want to have to use a loop, we probably want to do it without the loop, because generally that's better for time complexity and all that kind of stuff. Okay, so paste these guys in. Pleasant memories, great memories. But for now, we want to do something a little bit different. So we want to treat this a little more in kind of a more mathier way. Something I want to point out is by rounding up, I mean, there's okay, this kind of actually reminds me of one of the previous ones we did not too long ago. It was called addition without carries or something like that. Like, basically we were trying to add numbers and not carry, geez, what do you call those even? The carry numbers, you know the things I mean, the ones and stuff like that. Anyway, the point is, so we were doing something like that, and this kind of reminds me of it, because we're kind of, in some cases, like carrying over a 1 into the next number, right? Like in this case over here. Oh, I didn't even notice they had these nicely laid out here. Oh, well. Anyway, So we have this one over here. Basically the 5, we can think of the 5 as being rounded up to 10, and that the 1 from the 10 is being carried into the 4 over here. That's kind of one way to think about it anyway. I don't know, Rainbow. Would they be called remainders? Usually remainders is division, right? So, but yeah, I guess. I mean, it isn't part of the number. So anyway, we don't need to get into that. You guys know what I mean. The point is, we've got this number here, right? And because the 5 is going to get rounded up to a 10, like they're saying over here, that means the 1 part of the 10 is going to get absorbed into the 4. It's going to become 50. And then we'll do the same thing. This 5 ends up rounding up this 4. It's like carrying over a 1, so it becomes 5. And then because this is a 5 now, we carry that over to this, and it becomes a 2. But just like the addition without carry, something we noticed in that case is, well, in the case of the addition, we found that since we're adding, the biggest number you can get by adding 2 digits is going to be 18, which would be 9 plus 9. Whereas in this case, we're also only going to get a 1. You know, if 18 is the biggest number, the 1 is then going to be the biggest number you'd have to carry. So, but in this case, we're also going to get a 1 because we're basically either going to have a 0 or a 10. So we don't really need to worry too much about like how much this is going to be increased by, if it's going to be increased. Like it's not like this number or anything beginning with a 1 could get rounded up to like 3,000, let's say. You know, it's too much. Like it's either going to be 1,000 or 2,000. So it's within it's within like a range of 1,000. You know what I mean? Like it's not going to go outside of that. Okay, so the point is, moving along with this stuff over here, because this could only go up by a maximum of 1, I want to sort of think about this in a different way. So I'm going to take some inspiration from the way we did it down here. So I'm going to say let, I am going to have a leading number, okay? It's actually going to be the leading digit. I want to pull apart the leading digit. I want to get that leading digit. But the only way I can do that, or at least the way that I thought of for doing that, is to sort of get the power of 10 that this is going to be. So again, we'll do something like power, but instead of doing a loop to build it up, we're just going to go directly to our math tool. So we're going to say it's 10 to the power of, well, what exponent? Basically this exponent. The thing we would get if we did math.floor of math.log 10 of value. So we'll use a logarithm. That's what logarithms are good for. I mean, logarithms tell us what exponent we need to raise a base to get a certain power. So, you know, if we're talking about like, let's say 2 to the power of 3 is 8. So basically this is the same as like log base 2 of 8. Whoa, that's a weird 8. Anyway, it equals 3 because of this. You know, these are two like different ways of phrasing the same thing. So with that in mind, basically what a logarithm is an answer to a question like this. 2 to the power of what? That's meant to be an x. Anyway, 2 to the power of what is, let's say, 16. Well, 2 to the power of 4 is 16. So that's the same as saying what is log base 2 of 16. Okay, so that's basically what logarithms are all about. That's what they're aiming to answer. And Rainbow asks a good question here. Does value.length work? Because that would sort of shortcut this part here instead of having to use log. I mean, for sure, I could convert it to a string. There's one potential issue. No, actually, that's not a potential issue. I was thinking the reverse. If I was converting a string to a number, which basically in that case I would lose leading zeros, but we don't have to worry about that in this direction. Let's try that. So we'll say return value.length. I'm gonna guess it's gonna not work because typically, like, I think, like, we're asking for a method here, right? We're saying value, it's an object, we want to call one of its methods. So we have to ask ourselves, like, what methods do numbers have, right? Whereas when we're talking about a function, when we put it in here, or what was it we saw the other day? It was a regexp, right? When we were doing like a dot test for a regexp, we found that when we put in a number in there, it automatically typecast it. So that's because the number was the argument of a function. When it's the argument of a function, we can kind of decide what we want to do with it. Just like value is an argument of the function rounders2 over here. We can decide what we want to do with it. We can make a copy of it. We can modify it. But basically the idea is that over here, or over here more accurately, we're calling a method of, we're calling a method of number. So it's not just going to automatically try typecasting this thing in order to call its method. So we would have to do a .toString, or at least something like that, if we wanted to get that. So yeah, this has a length of 5, and really what we want is 10 to the power of that, right? So yeah, wait, no. That -1 actually is technically what we want here. And you know, now that I'm seeing this, at this point, it's not actually looking all that much more efficient than what we have below. I mean, I suppose we could do something like this, right? And just sort of shortcut the conversion to a string. But then, I don't know, at this point, I'm sort of feeling like, is it really saving us enough? Like, is this shortening it enough from this? To merit the lack of clarity that I feel that this brings about, you know? So let's probably just do it this way for now. We'll just sort of keep it within the realm of math, but hey, good suggestion. Thanks for bringing that up. All right, so we've got power over here. And well, is that working actually? I don't think we've actually tried returning it yet, so let's do that. Yeah, 10. Great, that's what we want. 1,000. Another 1,000? Yeah, there it is. Slippery devil. 10, 10. Okay, good. It seems to be working. We're getting the values we want. So what do we want to do with power? Well, basically, there are a couple things we could do, I guess. We could say, for this leading part, basically, we could just do a division, right? So leading would be like value. Actually, we're going to have to floor this, so let me just get that in here. Value divided by power. And that should just give us the leading thing, right? Yeah, the leading digit. Yeah, because we're basically, like, we take this, divide by 1,000, what do you get? Well, 1.234. Well, let's round that down. We'll take the floor of that. We get 1. So that's going to give us the leading digit. Okay, so this is the leading digit. In fact, I might as well just call it leading digit, not to be confused with our leading, like, part of the number down here, right? Potentially more than 1 digit in this case, but this one is just going to be 1 digit. So we'll call it leading digit. And that's going to be, yeah, math.floor value divided by power. Great. So then what's left over? What else is there? Well, we could say other part. Yeah, other part basically is just going to be value mod power. So why value mod power? Well, it's basically the leftovers, right? So if we were to take 1,234 and divide it by 1,000, the remainder would be 234. So this number mod 1,000 would be 234. This number mod 1,000 would be 445. So basically that's the other part. That's what we're looking for. Now, why is that so special? Why do we need the other part over here? Well, let's first check to see if all of this is working. And then we're going to see something pretty neat. I'm pretty excited about this. I hope you guys are too. Whoops, leading digit. All right, let's run that. And yeah, null because we're not returning anything. But we're getting a power of 10, an other part of 5, and a leading digit of 1. Well, that makes sense. Yeah, because it's just 15. This is a bigger number. Good. So basically 1,000 is the power, 234 is the other part, the leading digit is 1. That all checks out, man. That's all accurate. That's what I can see. Okay, good stuff. So that's what we want. Now, why do we want that, though? Well, basically, let's think about how these numbers are working. My claim is basically this. For the other part, as long as it's below, like, 4, 4, 4, 4, 4, however many 4s there are for the size of the number. As long as it's below that, then we should be fine. So like, let's take a look at, let's say the power was 1,000, right? So 444 is the number we want to compare to. Let's take this as our first example. 1, 2, 3, 4. Okay, so basically this is our number we want to compare specifically the other part, right? Or the thing we're calling other part in our algorithm. So this part over here, we want to compare these. And we just want to say, well, this 234, is this bigger than 444? And if it is, then we're going to do something about that. So specifically, we would add on 1 to our leading digit and then put it all together, sort of thing. But this is the thing to compare to. Like, this is my claim right now, is that by comparing to this number, we can determine whether or not we have to increment this. And you might look at that and say, well, no, that's not going to work. Like, yeah, I realize over here, okay, this is less than 444. We did not round up. Whereas in the 445 case, that was greater than 444. Therefore, we did round up. Okay, so it looks like I've got a pretty strong case at that point. But what if it was a situation like this? You know, what if we were looking at a situation where it was maybe like, just choosing another color there. Oh, and we got to turn the thickness back down. That's a close one. What if we had a situation where, like, this was, I don't know, like a 7. Oh, I made it too thin. Oh, let's say this was like a 7, but then this one was like less, and so is this one. So we wouldn't end up rounding these up, and therefore we wouldn't round up the 7. So this number, even though it is bigger than 444, it's not going to have that property we're looking for, because this is not going to round up to the next one. This is not going to round up to the next one. Well, hey, here's the thing. I know in this case over here, I know it ended up cascading like that this 5 ended up coaxing this 4 into becoming a 5, and that ended up convincing this 4 into becoming a 5, and then this ended up pressuring the 1 to become a 2. But in this case over here, we don't need any of that. It doesn't even matter what this is. This is a 7. That will definitely cause us to round this one up. So I think my claim is pretty strong here. If we can compare this to 444, and if this part is bigger than this, then we'll round up the leading digit. Otherwise, we will not round up the leading digit. So, yeah, won't 7 still go up, Rainbow, to answer your question? Yes. I was playing devil's advocate for a minute there. Anyway, so, okay. What do I want to do here? Well, basically, just to sort of structure this before we go any further, we're going to return something that's going to be kind of like leading digit times power. I think that's what we're basically looking for, right? Well, not quite. We're looking for that in half the cases here. So in this case, yeah, it was great. It was 1,000. In these cases, great. 10, 10. But the ones that aren't working, it's because we didn't round up. So we have 10, should have been 20. Over here, half 1,000, should have been 2,000. Over here, we've got 90? Well, that one seems weird. Wait a sec. Oh, yeah. I get it. Okay. Oh, I think we can deal with that. Yeah, that makes sense. After all, it's just like we increase the 9 by 1, we get 10. So 10 is like our leading digit. Okay, I was confused for a minute there because they weren't the same size of number, but it makes sense. Guys, it makes sense. Okay, cool. So let's go back to this. And we should probably make a decision about when we want to increase this thing. So basically, yes, we want to multiply by power. That much is pretty much for sure. But what do we want to do with that? Do we want it to be just leading digit or leading digit like plus 1? So we'll say, like, you know, we'll put the optional 1 in here, I guess. Or maybe let's even use a variable for that. So optional 1. Yeah, that's good. That feels good, right? Okay, let optional 1 be assigned the value of, well, basically something that's going to be 1 or 0. And what are we actually checking here? Well, basically, we wanted to check if the other parts, like 234, is bigger than 444. Or like if 445 is bigger than 444. Or if there's a smaller number, like this one over here, we want to check, is 5 bigger than 4, right? So we sort of need a number to compare to before we can actually get the optional 1, right? So we sort of want to say, like, other part, hey, geez, I did that before too, is greater than comparator, I don't know. And if it is, we'll get the 1. If it isn't, we'll get the 0. And we'll just say let comparator be assigned the value of 444 for now. We're going to change it, but yeah, okay, so then it works over here now because it's saying, well, is the 234, is that bigger than 444? No, okay, so we'll not increase it by 1, but this was bigger, so we will increase it by 1. Okay, cool, neat. But the problem is it's not working for something like this because it's basically saying, okay, we got 5. Is 5 bigger than 444? And no, it isn't. So it doesn't increase the 1, and we really should have. So, okay, we need our comparator to be the right size. Well, how are we going to do that? Well, I've got a clever way we can do that. Basically, the idea is we're going to use a 9 trick. 9 has all kinds of neat properties in math. So one of its properties is that if we take any digit, in this case it's going to be 4, but if we take any digit and divide it by 9, we're going to get a decimal number that's going to be like this. 0. And then a bunch of 4s, infinitely many 4s. 4s forever. Okay, so 0.4444444. And this could have been anything, you know, this could have been 5 and it'd be like 0.5555555. It could have been 8 and it'd be like 0.88888. And so, yeah, I mean, we're going to use this. It's not exactly this, but it's going to sort of provide the basis of it. It's a number with a bunch of repeating 4s in it. And then if we were to multiply this by power, like in this case, power was 1,000, right? So multiply by 1,000, well, that's the same as moving the decimal point 3 places, right? So it's a 1, 2, 3, okay? So it would actually then become 444.4, and I'm just, to make this a balanced equation, I'm going to multiply this, and we'll get rid of that decimal place. It's over here now. Okay, so we've got 444.444444444. And yeah, it gets kind of echoey. Anyway, the point is, okay, so we've got this, and we are very close to what we're looking for, like the 444, but then we've got the decimal point, so we don't necessarily want that going on forever. One way we could easily get rid of that is to just round down, right? Like take a Math.floor. We could also do something where we subtract from it, well, the thing we started with. So if we take away 4 over 9, well then 4 over 9 is the 0.4444444, so that gets rid of all this stuff that comes after. So that would work. And yeah, any way you want to do a Math.floor, whether you want to use the bit trick with like the 0 or, the bitwise or, that's fine. But this way is a lot more direct in the sense that we're just subtracting exactly what we know the extra part to be equal to. So we just take away the 4 over 9. And hey, we could even take this expression, factor out the 4 over 9, and it would become 1,000 minus 1 times 4 over 9. In other words, what we're ultimately looking at is something like 999 times 4 over 9. Okay? That's basically it. And it makes sense. It's kind of like, you know, take this 999 thing you've got, divide out the 9s, multiply them by 4s. That's probably the best way to think about it. Okay, so how do we get that? Well, basically we just do power minus 1. That's going to give us the 999 part, or however many 9s there are for that given power. And we're just going to multiply that by 4 divided by 9. And that's going to give us our comparator. So if we do this, it should give us our optional 1. We're then adding that onto the leading digit. This should be enough, I think. Let's see. There we go. So just checking to make sure it wasn't one of our other functions here. They don't have the name rounders, so that's fine. This is working. Okay, good. Nice. All right, so I like this. I think it's pretty smart. We could probably tighten it up a little bit. You know, like I was talking about this whole business of like, how are we going to get rid of the trailing 4444444s? But the thing about those is we don't need to worry about that because these are integers. So there's not going to be anything in between anyway. So we don't actually need to do that at all. We don't need to do this subtraction by 1. We could just do power times 4 divided by 9. Let's try running the tests on that. And what we find out is it still works. It doesn't really matter. So, I mean, if you think about it, comparator now is just this, right? So I'll show you something neat here. So I paste that in, and now we sort of have like an equation, right? Well, I shouldn't say that. It's not an equation, it's an inequality. So we've got this inequality, I'm trying to choose a cool color. Okay, so our inequality is we've got other part and I'll just use, I was going to say, like, I'll use O. I'll use the variable O to represent that, but then that looks like a 0. So maybe I'll use, I was thinking P, but then P for power. Oh boy. Okay, I'll use a P for this one and a T for this one. T for like tens. Like power of 10? I don't know. Anyway, so we'll say P is greater than T times 4 over 9, right? So there are a few ways we could do T times 4 over 9. We could do something like this, T times 4 over 9. But as you may recall, when we're multiplying fractions, we basically just multiply the numerators and multiply the denominators, right? So we do something like this. We multiply those across and we get something like P is greater than T times 4 over 9. Well, we could just multiply both sides of this inequality by 9. So we could get like 9 times P is greater than T times 4. Oh, that's meant to be a multiplication symbol. Oh well. Well, it's a lot nicer. I like that better, you know, no division involved. So we could just say 9 times the other part is greater than 4 times the power. Let's try that. 9 times the other part greater than 4 times the power. Hopefully I didn't mess anything up in there. I don't think we had to flip the inequality because we didn't multiply by a negative. So, ooh, there we go. So that's looking pretty good, I would say. Let's see, any other changes we want to make in here? I mean, like if you don't want optional 1, we could just like take this and paste it in here because we're not using it more than once. Something like power, we're really getting a lot of mileage out of that. We're using it a lot of times, so we definitely want to have that as a variable. Do we want to keep other part as a variable? Maybe not. I don't know. We're really only using it over there, I guess, right? So if we're only using it there, maybe we'll just put that in there. I don't know. Is that better? I don't know if it's getting better. Well, it's not because it's not working. So let's go back a step. Let me try running that again. So that was working. What did I do wrong? Oh, it's an order of operations thing. Hey, you know what? Let's just leave it like this. It's fine. But I do want to change these to constants because we're not actually changing these. We're not reassigning these at any point. So it makes sense for all of them to be constants. Let's make them constants. I feel a little better about that. I think there's a marginal memory optimization gain that we get by using constants because we allow the interpreter to make assumptions, right? So it doesn't need to be worried about like leaving its options open in terms of reassigning these variables. It knows they're going to be constants and that it would be, well, it would be erroneous to try to reassign them. So anyway, I think that's it. Did we officially submit this one? Yeah, okay, there we go. So it's official. It works. We did it. Congrats.